welcome to the deep dive. Today we're looking at something, well, pretty mind-bending. Hypervelocity stars. I mean, stars moving to our galaxy at maybe 500, even 1,000 kilometers per second, or faster.
It's incredible speed, yeah.
So the big question is, what on Earth, or rather what in the cosmos, could launch a star like that? That's what we're diving into.
It's a great question. And, to really get how weird these are, think about normal stars near us.
Okay.
They're moving maybe 20, 30 kilometers a second, sort of going with the flow of the galaxy.
Just kind of cruising along. Their speed is just from like where they were born and maybe some gravitational nudges.
Pretty much, yeah. Nothing too dramatic.
But then you hear about runaway stars. That sounds faster, like 100 kilometers per second, maybe more.
Right. Runaways are a step up. They get a bigger kick.
From what, usually?
Well, often it's a binary system where one star goes supernova, boom, kicks the partner out.
Okay.
Or sometimes, in a really crowded star cluster, stars can have close encounters, gravitationally speaking, and one gets ejected, slingshotted out.
And you can sometimes see like a shock wave in front of them.
Exactly, a bow shock, like a boat wake.
Okay, so runaways are fast, but hypervelocity stars, they're on another level entirely. Those kicks aren't enough, are they?
Not nearly enough. For those kinds of speeds, you need something much more powerful.
And that's where black holes come in. You mentioned they're the key.
That's the leading theory, yes. Black holes are these points of, well, unbelievable density. Collapsed matter with gravity so strong, nothing gets out. Not even light.
Right. Escape velocity greater than light speed.
Precisely. And we think most big galaxies, like our Milky Way, have a supermassive black hole at their core.
Supermassive, meaning?
Millions, sometimes billions of times the mass of our sun, all packed into a, relatively speaking, tiny space.
Billions. Wow. And we have one here in the Milky Way.
We call it Sagittarius A, or SGRA for short.
SGRA.
The evidence has built up over decades. It started way back in the 1930s with radio observations pointing to something really energetic at the Galactic Center.
Radio waves.
Okay.
But how did we get more certain?
The really compelling stuff came later. High-resolution imaging, particularly in infrared light, using huge telescopes, like the Very Large Telescope in Chile.
And what did they see?
They saw stars. Stars whipping around an invisible point right at the center.
You can actually see stars orbiting a black hole.
Well, you see the stars orbiting something incredibly massive and invisible, and a black hole is the only thing that fits.
Amazing.
There's one star in particular, S2. Its orbit is tiny, takes just 16 years to go around.
16 years. Around something that massive.
Yeah, and at its closest point, it reaches, get this, 7,650 kilometers per second.
Whoa! That's what percentage of light speed is that?
About 2.5%.
Okay, just,
Yeah.
wow. And tracking these orbits tells us the mass.
Exactly. By watching how fast these stars move and how tight their orbits are, we can calculate the mass of the central object, SGRA. It comes out to just over 4 million times the mass of our sun.
4 million suns packed in there.
Yeah.
Okay, so we've got this monster in the middle. How does that launch a star at hypervelocity?
Right, so this brings us to the Hills mechanism. Jack Hills proposed it back in 1988.
Hills mechanism, got it.
The idea is the supermassive black hole acts like a gravitational slingshot, but on a cosmic scale.
A slingshot, how does that work?
Imagine a binary star system, two stars orbiting each other, wanders too close to SGRA.
Okay, a pair of stars.
The black hole's gravity is so intense, and the difference in pull across the binary system, the tidal force, is huge.
Like tides on Earth, but way stronger.
Way, way stronger. Strong enough to rip the binary pair apart.
Rips them apart.
Yes. One star often gets captured by the black hole, maybe ending up in a tight orbit around it, but the other star gets ejected.
Flying outwards.
Flung outwards at incredible speed. Could also happen with a single star having a close three-body interaction near the black hole, but the binary breakup is sort of the classic scenario.
And that fling's powerful enough for hypervelocity.
Oh, yes. Simulations suggest ejection speeds of 1,000, maybe 2,000 kilometers per second, possibly even more.
That's definitely enough. Way beyond runaway star speeds.
Absolutely. And the fastest ones, they get enough speed to actually escape the Milky Way's gravity entirely.
Escape the whole galaxy, so they're just gone into intergalactic space.
Eventually, yes, on a one-way trip out.
Mind-blowing. Have we actually found one of these escapees or candidates?
We have. The very first one was found, actually somewhat by chance, in 2005 by the Sloan Digital Sky Survey.
Sloan. Okay. What was it called?
SDSS J0907. Rolls right off the tongue, eh?
Catchy? And what was it like?
It was a B-type star, relatively young and hot, and its velocity away from us, the radial velocity, was measured at over 800 kilometers per second.
800 kilometers. That's huge. Where was it?
Pretty far out. Estimated about 55 kiloparsecs away, so maybe 180,000 light years,
Right.
and way up out of the main disk of the galaxy.
So far away and moving fast. Did its path point back?
It did. When they traced its trajectory back, it seemed consistent with being ejected from the galactic center.
Ah, the smoking gun.
Kind of. The prediction was it should have very little sideways motion, proper motion, across the sky if it came straight from the center. People were really waiting for the Gaia mission to measure that precisely.
Gaia, the star mapping satellite.
Right. So finding that first one was big. But finding more, that could tell us a lot about the galaxy itself, couldn't it?
Oh, absolutely. These stars are like probes. Finding more helps us understand, first, the galactic center itself.
How so?
Well, how many are being produced? What are their speeds, their directions? That tells us about the stellar population down there near SGRA and the dynamics, how often these interactions happen.
Right, messengers from the core.
Exactly. And then there's their journey outwards. They travel through the galactic halo, this huge, diffuse region surrounding the main disk.
Okay, their paths are bent by the galaxy's gravity over vast distances. So, by tracking them, we can map out the gravitational potential of the entire Milky Way.
Including the dark matter part, the stuff we can't see.
Especially the dark matter part, because that makes up most of the mass affecting their paths. It's a unique way to weigh the galaxy and see how matter is distributed way out there.
That's clever, using these tiny, fast stars to weigh the whole thing.
And there's another thing. The precision measurements from Gaia for these stars and others also help us pin down our own motion better, the sun's motion.
How does that help?
If we don't know exactly how we're moving, it affects our calculations of the hypervelocity stars' paths and where they came from. So it all ties together.
It's all connected. You said they're rare, though. How rare?
Very rare. Based on estimates of the ejection rate from SGRA, you might expect maybe one within about, say, 3,000 light years of the sun. One.
Just one.
Yeah.
Out of all the stars nearby.
Yeah. So finding them is tough, like looking for a specific needle in a galaxy-sized haystack.
Okay, that really puts it in perspective. So after 2005, people started looking specifically for them.
They did. Dedicated surveys were launched, like one using the MMT, the multi-mirror telescope, looking for stars far out in the halo with really high radial velocities.
Scanning big patches of sky.
Yep. And they found dozens more candidates. 50, maybe 100 kiloparsecs away from the center. Other telescopes, like LEMUST in China, joined the hunt too. And sometimes Hubble was used for follow-up to get better data.
And then Gaia. You'd mentioned Gaia. That must have been a game changer.
Oh, absolutely transformative. Gaia measures positions, distances, and proper motions, that side-to-side movement with insane precision for billions of stars.
Billions.
So when Gaia's second data release, DR2, came out in 2018, astronomers could finally check the proper motions for many of those candidates.
To see if they really came from the galactic center.
Exactly. Trace their paths back much more accurately. Plus, Gaia's all-sky survey found completely new candidates that other surveys had missed.
So what did Gaia show? Did most come from the center?
It's looking like a mixed bag, actually, which is really interesting.
Oh.
Gaia data did strengthen the case for many candidates originating near SGRA. There's one called HVS-22, for example. Gaia makes it look very likely it was kicked out from the center at maybe 1,500 kilometers per second.
Okay, so the Hills mechanism is definitely happening.
Seems like it. But Gaia also found hypervelocity stars whose paths do not point back to the galactic center.
Really? Where are they coming from then?
That's the big puzzle now. It means there have to be other ways to get stars moving this fast.
Like what? Any ideas?
Well, one really intriguing case is HVS-3. Its trajectory seems to trace back not to our galactic center, but to the center of the Large Magellanic Cloud.
The LMC, our satellite galaxy.
Exactly. It's moving over 800 kilometers per second away from the LMC.
So, the LMC might have its own massive black hole doing the same thing.
That's the implication. Strong evidence for a massive, maybe intermediate mass black hole in the LMC's core.
Wow, okay. That opens things up. Are there other possibilities too?
There are. People had predicted Gaia might find hundreds of these things relatively nearby within tens of kiloparsecs, and Gaia DR2 did turn up more candidates. Some look like they came from the center, others not so clear.
And you mentioned white dwarfs earlier. Hypervelocity white dwarfs. That sounds odd.
SA's, right. But Gaia found 3 of them, these incredibly fast-moving stellar remnants.
How could a white dwarf get that kind of kick?
The leading idea involves type Ia supernovae, the kind that happen in binary systems.
Okay.
Imagine a white dwarf orbiting another star. That other star evolves, maybe dumps mass onto the white dwarf, pushing it over the edge until, boom, type Ia supernova.
Right.
The explosion completely destroys the star that blew up, but the white dwarf companion survives and gets an enormous kick from the blast.
Like the supernova ejection for runaway stars, but even more extreme.
Potentially, yes. And for one of these hypervelocity white dwarfs, its path actually traces back near a known supernova remnant.
Ah, more evidence.
Exactly. It suggests these extreme binary supernova ejections might be another channel for creating hypervelocity objects.
So it's not just SGRA. We've got maybe the LMC black hole, maybe these superpowered supernovae. Any other exotic ideas floating around?
People are exploring things. Maybe there are intermediate mass black holes, smaller than SGRA but bigger than stellar ones, hiding in the galactic disk. Could they do similar ejections?
Huh. Plausible.
Theoretically possible. Another idea involves galactic mergers. When smaller galaxies merge with the Milky Way, the tidal forces during that disruption could potentially accelerate some stars to hypervelocities.
Our galaxy's cannibalistic past creating speed demons.
Something like that. The picture is definitely getting richer and more complex than just the Hill's mechanism alone.
It really seems like these stars, as rare as they are connecting dots all over the place, from the galactic center to satellite galaxies to supernovae, even galactic history.
Absolutely, and it even pushes into cosmology.
How so?
Well, understanding how these stars move through the halo, like we said, probes the galaxy's gravity, mostly set by dark matter. That data helps refine our models of how galaxies form and sit within their dark matter halos.
Like the standard lambda CDM model.
Exactly. The motion of hypervelocity stars gives us real-world tests for those models, helping us understand the distribution of dark matter and the universe's large-scale structure.
So wrapping this up, hypervelocity stars are these incredibly fast outliers, many likely shot out from our central supermassive black hole via the Hill's mechanism. That seems pretty solid.
Yes, that's still the dominant theory for many of them.
But it's not the only story. Gaia and other surveys are showing some probably came from elsewhere, maybe the LMC's core, maybe survivors of type A supernovae, maybe other exotic processes we're still figuring out.
That's right. The story is becoming more nuanced. These stars are fantastic probes, though, telling us about the galactic center, the halo structure, dark matter, even galaxy mergers.
It really is amazing what these few incredibly fast stars can reveal about the whole cosmic picture. And it leaves you wondering, doesn't it, given all these possibilities and just how vast the universe is, what other completely unexpected crazy celestial events are happening out there that we haven't even imagined yet?
Always more mysteries to uncover.
Definitely something to think about. Thanks for taking this deep dive with us.